Hello class, and welcome to a new video in our thermodynamic series. Today's video is a little bit off cycle in that I'm going back and revisiting something that you should have seen in Thermal 1, but I feel that many people are getting confused with. And that is the relationship between entropy, reversibility, and therefore irreversibility, and heat transfer. Stay tuned and enjoy. Okay, so you probably remember from your study of Thermal 1 that you can quantify the entropy of a system, or the change in entropy of a system during a process. Let's call it S2 minus S1. That would be the extensive change in entropy for any given process. Let's call it entropy change. And that's extensive, meaning it's not per unit mass, but it's overall for any process. Is equal to the rate of heat transfer to the system during a process. Okay, so this is the entropy transfer due to heat transfer plus this entropy production term, which we've used in our analysis of exergy, for example. So all these terms are extensive. All these terms are total changes in entropy for a given system undergoing a process. And without loss of generality here, I'm really talking about a closed system here. In other words, there's nothing coming in, nothing going out. If we were to extend this to a open system, then I would have to take into account the entropy of the material coming in and subtract the entropy of the system component leaving the system. And that simply is going to, it's not going to make any difference in terms of the analysis that we're going to do here, which is, what matters in terms of entropy change, how it concerns heat transfer and irreversibilities. So the question becomes, what happens specifically to a system when there is no change in entropy? We've already seen, and you see from this very definition here, that if I have a process on that given system where the process is reversible, that means, and I should probably highlight here that note that sigma, the entropy production terms, is exactly equal to 0 when the process is reversible. And it's greater than 0 at some magnitude for any irreversibilities in the process, or for irreversible processes. Irreversible processes. Right? And so, therefore, looking at this definition here, it is therefore clear that if process is reversible, then, by definition above, sigma is equal to 0. And furthermore, if Q is equal to 0 anywhere during the process, then the integral between 1 and 2, which is the entire process, of dq over t, must also be 0, the integral of 0. And so, therefore, this implies that S2 minus S1 is equal to 0 minus 0, which is simply 0. And so, therefore, S2 is equal to S1, and that's the very definition of an isentropic process. Okay, isentropic meaning the entropy does not change during the process. So the conclusion is, if my process is reversible, which is what I got over here, and if there is no heat transfer, the process is adiabatic, then the process is isentropic. So a question comes up, what if I have an isentropic? What if S2 what if I start with an isentropic process? In other words, a process where the entropy is constant, S2 is equal to S1, so constant entropy. Does that mean, does it imply that the process is reversible and adiabatic? In other words, if you tell me that a process is isentropic, is that the same as saying that that process is reversible and adiabatic? And the answer is going to be a resounding no. In order to prove that, all I have to do is find you one such process which is isentropic and which is not reversible and adiabatic, right? That would mean, if I can show you one such process, that in fact the constant entropy does not imply reversible and adiabatic. So let's look at one such process. Okay, I'm going to look at a process of a piston, gas inside of a piston cylinder, where the gas is compressed isentropically. So consider an example. Piston and cylinder compressing a gas. Okay, so state one looks like this. Here's my cylinder, here's my piston. Okay, and my system is a gas within the piston. That's state one. And the piston is moving to the left, compressing the gas. So that at state two, I end up with something like this. Cylinder looks the same. Okay, and my piston is way up there now. So that my gas is significantly more compressed. I'm going to use a different color here to show that the gas got compressed and is now hot. That's my state two. State two. So clearly, looking at this process here from 1 to 2, you know, we know without even doing any analysis at this point that T2 is going to be greater than T1 and P2 is going to be greater than P1, assuming, you know, that the process takes place with no heat transfer and reversible, which is what we would have if the process was initially isentropic, right? So we can consider this process to be isentropic initially. Okay, here. This. Let's go with black here if I can do that. So let's have a simple TS diagram. Gonna have gas that looks like that. That could be my state 1, and that could be my state 2. And a TS diagram is a great thing to start on an example like this, because I'm looking at the changes in entropy here. So if I say that the process is reversible and adiabatic between 1 and 2, we've already shown that means that it's isentropic. Isentropic means that the entropy doesn't change. So therefore, the S value, or the X value for the axis on this little diagram, this little plot, must remain constant. That means I'm going vertically up on this diagram. I'm going to get something like this. So between 1 and 2, I'm looking at this. Now, that's the case of the simple isentropic model, where the flow, the process between 1 and 2 is reversible and adiabatic. Let's look at a different case right now for the same sort of thing between 1 and 2. And let's say we look at a real engine. So we all know that a real engine isn't going to be really reversible, in the sense that there's going to be friction between the piston and the cylinder. And that friction is going to manifest itself as an increase in entropy. Why? Because this guy right there, sigma, isn't going to be 0 in the case of a real piston. There's going to be some entropy production due to that friction, which is going to make that guy greater than 0. So on my TS diagram, for the real process, and I'm going to put that real process in pink here, things are going to look like this, right? That's going to bring me here at 2 actual. If all that happened was the effect due to friction between 1 and 2. Now, you're probably looking at this and say, yeah, of course, I understand that. And therefore, the process that has an irreversibility is necessarily not isentropic. And that would be correct if that's the only thing that happened. But I have power here over that process, right? I can do whatever I want. So what if, for that very same process, the real process between 1 and 2, that shows an increase in entropy, what if for that very same process, I sucked some of the heat out? I don't like that at all. Change that. I sucked some of the heat out. In other words, this is not a well-insulated cylinder while this gas is being compressed between 1 and 2, and I do that continuously. And I do it methodically, so that as I suck the heat out of the gas during compression, I maintain a temperature that would follow the line that I originally had for the ideal process between 1 and 2. Right? I can do whatever I want. If I removed some of the heat, I could conceivably end here. Certainly, as I'm removing heat, I'm going to have to start dropping on the temperature. I could bring it here, I can do whatever I want. So I'm going to pick the specific amount of heat transfer out of this cylinder to bring me right back there, So in this process that I'm inventing for myself here, I'm going from 1 to 2, and I'm ending at the exact same state point as I did in my ideal process. So in other words, with irreversibilities, friction, say in this case, plus heat transfer out of the system, I can get S2 equals S1 for this process. So if S2 is equal to S1 for a given process, then that process, by definition, is isentropic. I got myself a process that is internally isentropic. The entropy of that system remained constant. But of course, it is not a reversible process. right? Because friction would have taken me to this point right there. And it's not an adiabatic process because I've had heat transfer throughout the compression step. So I have just given you an example of one process that takes my system from a state 1 to a state 2 that is not reversible and that is not adiabatic, but for which the entropy remains constant. And therefore, that is an isentropic process. Now, if you were to look at the entropy of the surroundings in addition to what's going on internally in the system, then of course the entropy of the surroundings would also go up. Okay, but I don't care about the surroundings. I just care about my system. So it's an externally, it's a process that increases the entropy externally of the surroundings, but does not increase the entropy internally of my system. We're talking about the system here, and that's all that matters. So for my system, I have an isentropic process that is irreversible and non-adiabatic. That's what I needed to prove to you. This particular example dealt specifically with a closed system, but you can see that I could have the exact same thing with an open system, and even more dramatically so, right? Because now instead of having the heat transfer and friction or whatever reversibility being part of that process, I can also play game with the entropy that's coming in and the entropy that's coming out for, of the system, of the control volume, sorry, during that particular process. The result is the same. I can design or fabricate a process that's going to maintain S constant between between its two end state points for that process, while having irreversibilities and heat transfer present. Voila, that's what we needed to show. Hope you enjoyed it, and I hope that clarifies things a little bit for you. Take care and have a great day. Bye-bye.